Hey, this is going to be the last lecture of the semester on synthesis of mechanisms. So far we have, with the exception of chem followers and maybe determining transmission ratios of gears and belts. Think your project, a belt in series with a gear, where we had to do what is called number synthesis, find the number of teeth and pulley radii. So synthesis is designing, finding a suitable mechanism for desired function or functional relationship. And it can refer to finding the type of number of links, how we join the links together, and then finding link length, fixed angles, if we think linkages. Cams, again, we did synthesis on cams. It was a matter of finding the shape of the disk cam. Okay, so type synthesis, selecting the linkage or other linkages, cam follow gears, or combinations suitable for desired task. And this is where knowledge of existing mechanical systems is useful. And in general experience, there are databases, the 501 mechanical motions, and some of them made it online, where we can go and find inspiration, or the 101, although I think there are more than 101 mechanisms appendix to this class. Okay, so this is at very early stages. You choose the type of mechanism that will satisfy a given function. So let's go to some examples for car jacks, say, well, you could adapt a car jack to other functions, but in terms of what a car jack does, we have the classical one. Okay, so you remember there are gear sectors here, and we have the screw, the power screw, and it appears that this power screw in the original 1920s patent, it's where it's coming from. The inventor considered using a left hand and right hand screw, and then other designs. I think I've seen one of these in use, and then I had a car that it came with this kind of jack. This one was invented in the 1948 by a gentleman named Brown. So let's go to some examples, and this is, I have a folder here, toys. So and this appears to be a 3D model rather than a prototype. But if you have this covered, you wonder how I can, could be a design task, how I can get this mechanical figure move by the simple rotation of a crank. And you recognize 4 bars and gears inside, and there's we cannot tell exactly, so might be a matter of designing the mechanism that takes motion from the same crank and moves this to move the tail of the character. Okay, this I'm telling you, this is from some research sponsored by Disney. So animated characters are driven by linkages. And then question: how do you think this little toy is driven? So this would be one example, and then this other one. You press the button, and the crocodile extends and closes the mouth. So I have for both animated GIFs. Question is, how is this designed? Of course, you can reverse engineer it. You break it apart, or if you want to spare it, you put it on X-ray. Otherwise, if you have an idea, how do you embody that idea? How do you create the mechanism? What kind of mechanism you should consider to, like in this case, you have a sliding input. How do you make the arms of the character move? And mobility analysis is going to be helpful. So you do mobility analysis, and making sure that you have 1 degree of freedom in both cases, because you have one input for both. Okay, button pressing and this banana being lowered, so both go with one input. Okay, so you selected linkages and gears working together, and then you use mobility Grubel's formula to confirm that the number of links and joints satisfy the desired number of degrees of freedom. If you have just one input, the degree of freedom should be 1, with possible idle degrees of freedom in the actual. So if you're to analyze this for mobility and also include the how do you call these symbols of the character? Where is it? So these are loose here, so yeah, it will be additional 2 degrees of freedom from the motion of the symbols. Okay, but let's go to and continue. So number synthesis, confirming with mobility Grubel's formula the degrees of freedom, and then dimensional synthesis. You want a certain range of motion. Going back to this character, you want a certain range of motion for the arm of the character. How you're given a displacement of the input, how do you correlate them? That's a matter of sizing what's inside the right way. Okay, so we analyzed for mobility, taking, and it's something that I believe I mentioned on occasion. So using the building block concept, and so instead of working with the individual links and individual joints, we work with groups of links and joints that we know, if added to an assembly, they don't modify the existing number of degrees of freedom. So I invite you to go back to those the early notes, and I think we considered this animated character, and we recognize, for example, that the arm, assuming this is just a rigid connection, so I have 2 links and 3 joints, and if we include this in the analysis, mobility analysis, then either having the arm or not in place does not change the number of degrees of freedom of the character. it can pivot about this point. There is a friction wheel inside that drives the tricycle front wheel, and then again, assuming this is rigid, we have the same story here, although this is immobile or moves together with the entire character. So I have here 2 links and 3 joints, and we can take the entire right leg off, and Pinocchio will still move in the determinate fashion. Will be just the outer, and you could induce some input motion to a bicycle by working with just one leg. So mobility doesn't change if I'm removing one leg, which consists again of 3 links, or other 2 links and 3 joints, and this is a dyad. This dyad RRR, and then we have RRP prismatic, so rotation prismatic, or TRRT translation. And these are the possible dyads with 2 links and 3 joints here listed. Of course, who are in practice, you'd rather see the RRP dyad with the sliding block. So the dyad the RRP type is going to be, it's rather going to be one where the piston or the slider and the pin joints are overlapped. There's no offset, and for good reason. With an offset, you induce a moment of the slider relative to its guide. Okay, so building blocks, it's helpful because you can formulate linkages faster, and then you don't need to check Rubel's formula all the time. So if I have an input that is a crank, and that is a crank that is hinged to the ground. Okay, so let's go this way. So I have a crank to the ground, and say it's powered, whereas the input is a hand-driven crank. And I have 2 ground in the actual link, 2 links in 1 joint with 1 degree of freedom. Mobility is 1. If I come in with these, the RRR dyad, and put it in place, and then connect to the ground, I get that good old 4-bar. Okay, and then I could continue with have an offset point, and I can come in with the other dyad that we looked at, very common, the RRT dyad, so I can put it in place. And this is the one that you did for one of your into the ground for one of your tutorial working model tutorials. So again, this is a ternary link, solid link. I have 1 input as separate units. These have 0 degrees of freedom. We call this potential joint. Potential joint, there will be potential joint at the slider. This one is potential joint. So having 0 degree of freedom as by themselves, you add them to the original 1 degree of freedom crank, the simple mechanism. You made the 4-bar. You came in and further amplified to, this is a Watt2 linkage, was a translation prismatic joint. So I know that by doing so, the mobility is not altered. So rather than doing try and error with links and joints at a time instead of building blocks. Um, okay, and there are complexity of analysis. If you're to do vector loop equation, it's not tractable in closed form analytically. But there are building blocks more complex. This is the triad, and this is the tetrade, and there are others, multi-tetrade and hexades, and everything becomes complicated. Still useful though for synthesizing planetary transmission, complex one with multiple planets, because we can get the equivalent of a gear pair using linkages, and I believe we discussed that. Okay, and some examples where you start with a and this is the one that I drew in Paint. Okay, but you could expand with a second diode that's not connected to the grounding, but rather to one of the to the coupler at a coupler point. And this is a Watt 2. This will be a Stevenson. This is the Stevenson 3 mechanism. Okay. This is also Watt 2, but driven from the Turney link. This is where it's triad, again the crank, the original simple mechanism that we amplified with triad, and it was a dyad and a tetrade. Okay, for dimensional synthesis, so talking linkages here, mainly. We want to find link lengths and possibly or fixed angles of links, like here, how big this angle should be, this angle, and in order to achieve the desired motion. And we learn about cognates and equivalent mechanisms, and knowing that they exist, it's useful. So how do we do dimensional synthesis? Say you have what? You have a 4-bar and playing with. Looks like it's slower when I'm recording. Okay, so I have a crank, and I hit run, and then I want to do a build a 4-bar, and does very well. So I and then to make it in a 4-bar. Link to the ground. This might be too long. I never get it right to where it's a crank driven. So join, and then but I can make it longer. Can I? Well, not by dragging, but rather so I can make it 4.5, and I can make it shorter to be on the safe side. Let's say just 2, and okay, so we've got a 4-bar. Cross fingers is a crank rocker, and it is. But we want to get certain oscillation, angle of motion to the output, and we've been there. We have been there. Although you can have applications where there's a given angle of swing the input, and you want to get certain angle of swing the output. We'll look at some problems. So, but we can use trial and error, quick exercise of working model. But we can define define controls, and we can have so height. Okay, so I can adjust. Oh, I'm sorry. I was supposed to be width. So define new control, width. Okay, and I can use a meter and so measure, and then rotational graph, and or other means to see what the angle of swing is for the output link. And I could do the same. I can define a control and increase the width. Okay, and including for the ground link, I can make it so measure, rather define U control and its offset. Okay, X and Y offset. All right, and hit run and spend this or do this repeatedly for one whole afternoon before I invest on designing the links and sizing the bearings and building a prototype of a say 4-bar that is crank driven and oscillates, maybe a drying fan on a car washing machine, or a if you remember, we had we discussed this, the let's see, I have it, is it on kinematic chains? Okay, so this is a 4-bar. It's a 4-bar that actuates the brake of a wheelchair. I was looking for it's somewhere, might take longer too, or an example about sizing a 4-bar. For sure, it's a 4-bar view where you have the pedal travel and you have the lead travel of a trash can, and there is a 4-bar inside that you would like to correlate. The pedal travel was the near 90 degree, which will be short, maybe 20-30 degrees to almost 90 degrees opening of the lead. But I was looking for, and I do have it somewhere, was, yeah, fans. The oscillation of a fan that is crank driven, and this is a drag. Is it a drag link? Yeah, drag link, Grashof 1 drag link. But you want to get a certain amplitude to the oscillation of the fan for continuous crank input. How do you do this? Trial and error, but you will see there are other more effective tools to use. So trial and error 1, we'll look at some graphical methods, and if you can do it in AutoCAD, high precision, that's preferred. And then there are analytical methods. We learn how to do analysis. So everything was given, link lengths, and all that, and we wanted to calculate correlation between output and input. Here we can impose correlation between input and output and leave as unknowns of the link lengths. And we can use design charts. There are design charts. I spent time generating charts for sizing steering mechanisms. And there are others for sizing, and not only, actually not very long ago, to size hydraulic actuation that are higher efficiency by including mechanical advantage and transmissioning. If you can tell, so we looked at trial and error, if you can tell the computer how a mechanism is better than the other one, then the computer can do the trial and error, and in a guided fashion, although random search is not excluded, and select the best solution after very many trials, way beyond the limits and abilities of a human operator. All right, so before moving forward, I'm going to present this concept of scale, rotation, and variant. We discuss about knowledge of cognates, mechanisms that have different link proportions or equivalent mechanism. They have different structure, and they can generate exactly the same curve or input-output correlation. Here's another property very useful. So we have scale invariance. If you have, if of concern is the correlation between theta 2 and theta 4, then absolutely the same correlation holds between a smaller or a bigger 4 bar. And it makes sense, number-wise, I can measure links in millimeters and then in inches. The millimeter will be more numbers, but the ratio between the link lengths, corresponding link lengths, is the same. But physically, you can have a smaller 4 bar and a similar 4 bar that is bigger. Correlation between input and output is the same. And then we have rotation invariance. And actually, was my experience working with a group of students that they figure out a hydraulically actuated arm, but they wanted to have the drive a point C. They wanted to have O, B, and C inline. I said it's better if you can offset B to maintain the strength integrity of it was a structural piece of box tubing. So if you do this, if you're taking the triangular loop OBA, OAB, and you rotate it, in this case was clockwise, just the triangular loop by angle beta, so this point will, by rotating by beta about O, goes from where it was here, and then point B rotates about O by the same angle beta. You'll get the same the same swing less phase angle for link OC like you had original. Okay. Very important, very useful property to be aware of. Again, I had to spend time explaining the students that you get exactly the same input-output, from input being hydraulic cylinder, output being angle of swing of the rocker. Okay, so graphical synthesis. There are some graphical techniques, that I included in my notes. So let's look at one that allows us to size a hydraulic cylinder that will have best transmission angles and satisfy the desired angle of swing for a given minimum maximum length of the hydraulic cylinder, of the actuator. It could be pneumatic actuator or linear actuator that is electrically driven. So I have L min, L max. You start with hydraulic cylinder, and you want to get an angle of swing, say 80 degrees. Okay. And L min is some number of inches. L max, it will be bigger swing or delta L, delta S of the actuator comes from the difference between the two. Okay. How do you get it? How do you get the linkage? Would be one of these, but now we want to get the best transmission angle, like I said. So the procedure is as follows. You draw the output link in its limit position. Okay, so you get this angle was the vertex at B. You connect A1 and A2, find the middle, draw the perpendicular from B to the line A1, A2 would be at the middle, and then extend. Do I need this? I don't think we need this. By the way, it's 11 o'clock in the evening, so I'm a little bit slow in observing things. Sorry for that. So what we do, maybe if I take a screenshot. Yeah. Okay, so select all, paste, and so we start with the hydraulic cylinder, I said. Okay, so, and then the long version, copy paste. So I have let me clean it a little bit. Okay, so hydraulic cylinder, and of course will be the longest version now. Could have prepared this ahead of time, but I know you can fast forward, or can you? Alright. And then what I'm after is okay, so I believe I started saying it the wrong way. Okay, so we start with the actuators, and you take it the shortest and longest, and you put them in line like so, and then you want to get point B. So you don't start with point B. It's actually start with actuator, and it'll be A1 and A2. A1, A2. That's why I started saying find the middle and draw the perpendicular. So you draw the perpendicular to the middle of the segment A1, A2. And then what's left is for you to find where point B is, and if this angle is, we start considering 80 degrees, you take half of it, it's 40 degrees, so you it means that this will be 50 degrees, so you go and measure 50 degrees here. Okay, this will be 50. This makes the angle 40 degrees. Not that it is on my drawing, but I'm just saying. And that will get you point B. And then you can complete the mechanism if you want to sketch it into the limit positions. Okay. So, and this also ensures minimum deviation from 90 degrees of the transmission angle. In the middle position, so halfway between leftmost and rightmost position, I get the minimum transmission angle, and then. And the transmission angle, by the way, let me change color. So transmission angle is going to be this one. And it's also going to be equal to, in terms of deviation from 90 degrees, so this angle here, if I'm to draw down, so this is 90, this angle here, it's equal to this angle here. And then on the other position, I have transmission angle is going to be equal to this angle. So these properties ensure, again, that the way we drew it, we made this construction, ensures that I indeed get the angle of swing that I want for L min and L max, and also have minimum deviation from 90 degrees of the of the transmission angle, and that's actually this deviation, it's equal to half the angle of swing. So for 80 degrees angle of swing, I get transmission angle that is 90 degrees plus minus half of this, 40 degrees. So suddenly we can tell what the maximum angle of swing of this could be in order to stay within the recommended limits of the transmission angle. So if I want the transmission angle to be plus minus 45 degrees, then I cannot go more than 90 degrees angle of swing. If I go plus minus 60 degrees, this could be 120 degrees maximum angle of swing. Okay, and if you can hear any background noise, I apologize for that. All right, so this was for very important hydraulically actuated hydraulic actuation. You can see them everywhere. Bulldozers and excavators, and might not follow exactly this this construction. This works for overcoming a constant load torque at B. If you were to manipulate something in the vertical plane, story is a bit different. Okay, 4-bar mechanism driving the coupler through two positions. This is a rigid body guidance problem, and we want to size the 4-bar. And examples could be, if I go to the notes, examples could be it was a tough semester or end of semester. So we're at synthesis, and I have some figures and some examples. I believe I brought this up at the beginning of the semester. How is this the mechanism that drives the shear design? We can research, and it will be a spatial mechanism for sure, because the rotation of the motor is in plane with the, not perpendicular to the plane of the shear motion. I'm looking for some figures showing garage doors, and it might be the, okay, let's see, kinetic chains. Gosh, should have scheduled this for so K, kinematic chains. Okay. It was here. It wasn't. Like a garage door. Okay, so example of a garage door that I'm missing like right now. I was certain it's somewhere. It is an example where, and of course I'm not in front of a whiteboard. Is this paint? No, where's paint? Select all. So you want to have, let's go this way. So you want to have a garage door that has to go from closed to an open position. Okay, two positions. And I want to use a 4-bar to guide it between these two positions. Could be a furnace, could be a furnace, yeah. That was my child trying to get in. So could be also a furnace door, and I want to find a 4-bar that can take a coupler and move it between this position and this other position. So I have I have points A. Come on. I have A1, A2, I have B1, I have B2, and A1, A2, and then B1 and B2. How do I get a 4-bar? Well, changing colors, and you just connect, could be thinner line, you connect B1, B2, A1, A2. Alright, find the middle, draw the perpendicular to the middle, and likewise here, find the middle, draw the perpendicular to the middle. Well, even in Paint, I think I can, yeah, I can take this and move it in the middle. I'm not looking at the intersection, although that could be a particular solution to our problem. I'm not looking at the intersection of these two lines. I'm just saying that I could have one of the joints anywhere along this line and the other ground joint anywhere along this line, including, if I place it here, it would be like moving can we talk about that? Yeah, it might be a possible solution where the two ground joints coincide. So I have a 4-bar. It could go, say, I picked, actually no, it will be like here. That was a spline. So for first ground joint, I go from A1 to the point, and then for B, so the 4-bar will be this one that you see here. It's not responding. Hey, because it's in record mode. So this will be one ground joint, and I have the other ground joint. Okay, so be assured that with this 4-bar, I can take the A1 or AB coupler, and I'll get it in the new position. And so that will be O1 and A02, I believe we have, and this is explained in the notes. So first position, second position of the coupler, connect the corresponding points, draw the perpendicular, pick up points along the perpendicular, connect the corresponding points B, draw perpendicular, find the other ground joint, and the 4-bar will be guiding the coupler AB through the desired positions. We can go with 3 in post position, and in this case there's just one and only 4-bar solution, not for 2 in post position. We could have chosen ground location anywhere here and anywhere here, but you will see for 3 positions. And if I want, I don't have the freedom to offset, say this is the garage door, and you don't have to have the joints A and B right at the ends of the garage door. So if I can get along and offset, I get additional freedom to size the mechanism. But if we impose A1, A2, B1, B2, and I want the joints to be at A and B, for 3 positions, there's just one solution, like I said. So we have the coupler A1, A2, A3. We connect A1, A2, A2, A3. Not that it couldn't be A1, A3, but I need just 2 pairs. find the middle, draw the perpendicular, find middle, draw the perpendicular. Where the two intersect, it will be one of the ground joints. Likewise for B, I take B1, B2, B2, B3, draw the perpendicular, draw the perpendicular. Where they intersect, I have the other ground joint. The 4 bar, that is solution to my problem is just going to be, and I use red, it's just going to be this one. Okay, and this one. So this is the 4 bar, and guaranteed will take a line AB and will be exactly driven through this second position and through this third position. So this was a third actually graphical method. Analytical methods. This is where we write equations. And one example that we analyzed for displacement and time ratio, it was the quick return. But there we had the link length, and actually it was enough to know the ratio between R1 and R2 to tell the angle of swing and the time ratio. And we can take those equations and now go in reverse. If I want to impose the time ratio, what should be ratio R1 over R2? Or if I want to impose the angle of swing, what should be R1 and R2? I cannot impose both time ratio and angle of swing because I have I'm limited. There's just one parameter to play with, that is R1 over R2. So we're taking the equations that we worked with when doing analysis, and so time ratio is going to be, as is shown here, pi over beta in radians, and beta is this angle here. It has the name theta min. And say I have time ratio 1.15, I can solve for beta, and then further using geometry in this right angle triangle. So I have what was it, R1 or the R2 over R1, that's equal to cosine of theta min, which is beta. And I can solve for, again, so going through beta, cosine beta, I can get the ratio between R2 and over R1, or R1 over R2 will be the flip fraction. And then we can calculate the resulting angle of swing. Okay, and I'm repeating, or the text here says what I told you earlier, that moments ago, that you cannot impose both the time ratio and the angle of swing. If I want instead, not a time ratio, but rather want a quick return with a given angle of swing, then likewise I can solve for beta, and I can go here and find the ratio R2 over R1. Okay. Remember the scaling invariance. So whether it's this size or I make it one story high, the time ratio and angle of swing, theta max minus theta min, will be the same for both. Similarly to using feet and millimeters. Feet will be few fractions, maybe. Millimeters, very many of them. And then arbitrarily assigning different units. That is changing millimeters to inches. Okay, for a 4 bar, we also analyzed in early in the semester the 4 bar, the crank driven crank rocker 4 bar for time ratio. Things are a bit more complicated here, but we could list the equations. So it will be 1, 2, and 3. Equation I have alpha 1, alpha 2. and then I could just go ahead and impose the condition for the mechanism to be Crank rocker Grashof 1. It's what you're seeing here. And then we need to solve it. There's no other option but to solve it numerically. So these equations, together with the condition for the mechanism to be Crank rocker, so this way we get the 4 bar with the desired time ratio. If we want, instead of a given angle of swing, then I combine these two equations, 3 equations here, with the condition for the 4 bar to be Crank rocker. Okay, so this is where the discussion extends to taking a 4 bar that is not crank driven. It's just you want to have a correlation between the input ground link and the other ground link, and could be the example of a small aircraft, and this is the stick, and you push the stick, you lift the control surface, you pull the stick, you lower the control surface, and you want to size the entire 4 bar given the angle of swing for forward and reverse. So I have essentially 3 positions of the input link in 3 positions of the output link, and these 3 are imposed as forward angle, that is push angle, pull angle, lift angle, lower angle for the control surface. And there's a numerical example. You have the freedom to choose the fixed angle here as well as this one, right? You can have this lever sticking at different angles off the control surface, and you can bend the actual stick, pilot stick. This one goes between the legs of the pilot. Not all aircraft have this kind of control. The smaller ones, they do. Fighter planes are the same. Commercial airliners, that they have a different means of controlling the surfaces. Okay, so we need to assume theta to 0. We need to assume theta for 0. In addition to being imposed, so we assume that, but we are given the forward angle and forward and the backward angle, and likewise for the output link. Okay, so the text of the problem says that backward travel are 42 degrees. So it goes 42 and 40, and the control surface goes 30 and 35. Negative would be, okay, so negative 40 goes with negative 35, positive 42 goes with positive 30. So I'm showing these 3 correlations of angles. Again, I chose, you could have or could have chosen, instead of 92, maybe 88 or 90 or 93, and likewise here instead of 75 other angles. But the other pairs were imposed. So 42 with 30, negative 40 with negative 35. And we're going to use a technique developed in the 50s by this gentleman. And so what do? We take the equation from a 4 bar linkage analysis, and we do some changes of variable, introduce H1, H3, and H5. Okay, and these are ratios of linked links, and then H5, it's a bit more complex. So a change of variable. And we repeat this equation. We repeat this equation 3 times for the separate thetas, theta 2 and theta 4. And we're going to get a system of 3 linear equations with 3 unknowns. So Freudenstein change of variable allowed this equation to turn into a linear one with the H1, H3, and H5 introduced. You solve for the three H unknowns, and then ultimately you can find the ratios R1 over R2, R1 over R4, and the individual lengths. Should have mentioned for this 4-bar, the base length, the length of the ground link was imposed, and of course you should consider playing with different initial angle, theta 20, theta 40, until you get favorable transmission angles, and of course the resulting 4-bar, it's a satisfactory one. You don't want to have it too tall that goes outside of the cockpit of the airplane if it is an airplane that the application pertains to. Okay, so really you repeat this equation 3 times. You solve for H1, H3, H5. If I have R1, I can solve for R2. If I have R1, I can solve for, and the H's for R4. And then lastly, I can solve for R3 from this 3rd equation. Okay. This can be extended. This technique can be extended to generating 4 bars or synthesizing 4 bars that can approximate a given function. I'm not emphasizing this much. The applications are fewer now for mechanical function generators. There were more of them in the past. Is not responsive. So we have what? We have barometer as function generate, mechanical function generate, steering mechanism. We also have exact function generators, linkages that exactly produce like a Geneva Scotch yoke. So and this was 3 precision point technique. We can impose precision points such that the motion of the input link is the independent variable, the motion of the output link is the function you want to generate. Here's the example of an x squared. And all I need to do is to say, get this function exactly approximated at 3 locations, and with the hope that in between the deviation won't be that much. It doesn't help if we impose the limit position as exact positions and one in the middle. It's best if we start inside and the other exact position, the third one is not as before the limit position occurs. And this is explained here, how to correlate firstly angles of displacement of the input and output links with the variables. You want to have linear scales. That's essential because we can better interpolate on linear scales versus, you could just take any 4-bar, any calibrate, but it will have divisions that are spaced unevenly both for the input and output. So yeah, we want to have linear scales for both x and for both y, the function. So that's one step, and then is a matter of placing that precision points. And instead of, I said, having the end points in the middle, you have the middle, yes, but then the other 2 points would be obtained using what is called Chebyshev, like in the Chebyshev polynomial spacings. And for 3 points you get it like so. You inscribe a hexagon, and this is where the first precision point is, second precision point, third. So not exactly at the end, at the beginning, not exactly at the end of the range of independent variable, and it gives you good or improved precision in approximating the desired function versus just taking the ends again. It's like having a balloon and you squeeze it and you want to have not too much bulging in between, sort of. Okay. And there's an example here, or the example is continued and is verified with working model. And this is about it. You have what? You have the desired function, and then you have the actual desired function you want to approximate, and what the mechanism is capable of doing. And this is error, and error in percentage, which is pretty good. This was for x squared. Okay. All right, so almost done. Some sample problems. Garage door. Example of type synthesis. In a regular semester, don't forget we lost one full week. I was having students do a homework of this type and then this problem. So these two problems were homework problems for students, and I added some other here for two positions with a 4-bar, and I'm just going to stop here. It's 11:30 in the evening. It doesn't mean that you're not going to see problems from this chapter at the final exam, and strongly advise you to try of the sample problems that I have listed here and ask me any questions that you might have. So I'm stopping recording. It was a fun semester, and if you're graduating in May, have a fruitful career. Don't forget to write donation checks to your alma mater. All right. Goodbye.